In this video, we are going to look at reaction mechanisms. Specifically, we're going to look at general reaction mechanisms in chemistry, and then we're going to look specifically at the Lindermann-Hinshelwood unimolecular reaction. And then we're going to end by looking at the Michaelis-Menten mechanism, which applies to biological systems. Okay, so firstly, reaction mechanisms. So essentially, reaction mechanisms are a set of steps that tell you how, that explain how a process occurs from reactants to products. And it explains, or it's consistent with the rate law. We've seen the rate law already. So it's consistent with the rate law. It consists of a sum of elementary steps, and elementary steps are unique insofar as the order of reaction in an elementary step is equal to or equivalent to the molar coefficient in a balanced chemical equation, which is pretty unique because that's not usually the case. So only for these are orders of reaction. Do orders imply molar coefficients? Okay, so that's worthy of our note. We will see intermediates. Intermediates are something I don't think we've seen in previous videos. We've looked at transition states in previous videos, which are non-isolatable, high energy chemicals. Intermediates are isolatable, they're stable, but they're somewhere chemically in between a reactant and a product. Okay, so there's some information there generally about reaction mechanisms, so I'll scroll down to remember to get rid of my annotations, which won't follow us, unfortunately. Okay, so obviously, like in any experiment, you have to agree with the data. So whenever you propose a mechanism, it has to agree with what you see in the lab when you mix chemicals together. And even if you have a mechanism that you think agrees with the data, it doesn't mean it's necessarily correct. There could be more than one potential mechanism that would explain the data. So you have to be very careful and cautious when you claim that you found the mechanism. You've only ever found a mechanism that explains the data. Okay, so let's take as an example this overall reaction. We've got 2 lots of nitrogen dioxide, give 2 lots of nitrogen monoxide and molecular oxygen. We are told, we do an experiment and we actually observe in the lab that the rate law, so we can see the rate law over here. So the rate law is second order in nitrogen monoxide. So it's a second order rate law. Now, caution, this coefficient, this exponent 2 here has got absolutely nothing to do with this molar coefficient. There's no link whatsoever. It's just coincidentally the same number. So somebody proposes a mechanism. So in step 1, they propose that overall, if we look at the overall process, then the proposition is that we have 2 lots of NO2, give 1 lot of NO and then NO3 with some rate. And then in step 2, the NO3 generated at the end of step 1 is then further decomposed into NO and O2 at some other rate. And obviously, when we combine these back again, then, you know, if we combine these back again, then the product NO3 in step 1 would cancel the reactant in step 2. And then we're left with just 2 lots of NO2 as a reactant, and then 2 lots of NO as a product, and then O2 as a final product, which is exactly the overall reaction. Okay, so this agrees. This so far would, if it were right, would return the overall reaction. But what about the rate determining step? So we're told here the rate law depends on the rate determining step. In fact, the overall rate law is equal to the rate determining step rate. So basically, the overall rate is only as fast as the slowest step. So I don't want to get ahead of myself with these notes. We'll see, but keep this in mind. This is definitely something I would retain in my gray matter if I were you. So overall, the rate is only as fast as the rate determining step. Okay, let's scroll onwards. Okay, so we can see here a diagram of steps 1 and 2 from the previous page. So again, if you're my student, hopefully you're following along with the notes that I posted for you, which I'm reading now, so as to give you the experience of being in a class with me. Okay, so we have step 1, which is where we took, I think this was NO2, right? Just let me remind myself what the overall reaction was. Yeah, so this was an NO2, and this was an NO2. Just to remind you what the overall equation was. The overall equation was 2NO2 to give 2NO plus O2. So that was the overall equation. So in step 1 here, we've got the 2 NO2s, and that was giving an NO and an NO3. Okay, these are the 2 products. This thing in the middle is obviously one of the oxygens that has been lost. We obviously can't isolate that. But actually, no, it's not an oxygen that's being lost. Well, so we're essentially going to, well, actually, am I right? Yes. So imagine that this dashed line here is a broken bond. So we're breaking this interaction here, and then we're forming this interaction here. We've done neither nor, but this is the process that's happening. So one of the NO2s is going to lose one of its O's to form NO. The other NO2 is going to gain the O to form NO3. But this would be the activated complex, which would be the double dagger that we see here at the top of the activation energy. So this activated complex is symbolized by a dagger, double dagger. And then eventually we get product and intermediate. So the intermediate here we can isolate. So we can isolate this. And we'll see in a second, it's actually right underneath this field of view now, that would be a saddle in the reaction profile. We'll see that in a second. So that's step 1. And then to go over and look at step 2, we've got NO3 let's see, which looks like this guy over here. So this would be NO3, where we've got bonds breaking and forming. That's what these dashed lines represent. And then we're going to essentially make NO2, NO, and we're going to form O2. So this would be O2 here. We've got two NOs here. Okay. So that's just to try and orient you a little bit about what's going on. And then if we come down, we can actually see the reaction profile, which is great. It's going to be useful. So just to annotate this pretty quickly, we've got energy against progress of reaction. We can see we're given some extra information in this thing here. We've got an activation, transition state here, an activated complex. We've also got a second transition state or activated complex here. And these are non-isolatable transition states. And here we've got the intermediate. Now the intermediate is a saddle point, which would be stable, and you can isolate that. We're told here that step one is slow, and you can see why it's slow, because its activation energy is much larger than in step two. So to go all the way from down here up here, you can imagine takes a lot longer, metaphorically speaking. Imagine if this were a hill, to use a crass analogy. You know, if you had to climb that hill or climb this hill, which hill would take you the longest to climb? Clearly the first one, but that's a crass analogy. So long as you only know it's not really a hill. Okay. So clearly the rate limiting step or the rate determining step is step one. So this is the rate determining step. Okay. We said on the previous page that the rate determining step is the rate overall. All right. We said on the previous page the rate determining step is the rate overall. And just to remind each other what that first rate was. So we know now that this is the rate determining step. Okay. And we know it's elementary, so I can read into what this coefficient 2 means. I can use it directly as the order. So the rate is going to be a rate constant concentration of NO2 to the second order. So it's second order in NO2. Okay. And you can see here that that's exactly what we knew the overall was, and that's exactly what the rate determining step rate is also. Okay, so that's straightforward. Okay, so this is just so this is an extension of these ideas. Now we saw in the previous example that we had an intermediate. The intermediate was NO3, if I remember correctly. Yeah, the intermediate was NO3. So previously we had an intermediate NO3. Fortunately, however, the intermediate NO3 was not in our rate expression. But what if your intermediate is in the rate expression? Well, the problem with an intermediate is you can isolate it, but it's constantly being consumed and produced. So your ability to know its exact concentration is limited. It's error prone. So whenever we have a case where we have an intermediate in the rate determining step, we have to use some algebra to manipulate the equation so that we don't actually have the intermediate in the rate determining step anymore. Okay, so take this example. So we can see here 2 lots of nitrogen monoxide gas and molecular oxygen give 2 lots of nitrogen dioxide. We're told a priori that the observed rate law is a rate constant, second order in nitrogen monoxide, and first order in molecular oxygen. We propose a mechanism. So the proposition is NO plus O2 gives NO3. And we can write, again, because it's a mechanistic step, it's elementary. We can assume, because of this 1-to-1 mole ratio, that it's first order in both of these elementary ingredients, NO and O2 respectively. And then step 2, we're told, okay, take the product of step 1, add more NO, and then you get the final product, 2 lots of NO2. So here, again, we can take the elementary steps, the coefficients become orders in our rate law. So it's another rate constant K2, NO3 first order, NO first order. Okay, so far so good. We're told that, or we're told at least the proposition says that step 2 is the rate determining step. Step 1, on the other hand, is fast and reversible. Typically, if you have a fast and reversible step, that's a good indication it's not rate determining. Oh, didn't want to do that clearly. How to get rid of that, though? I just drew it, so I must be able to get rid of it. Nope. Maybe if I select it. That's odd, is it? Don't know how I wrote that without meaning to. Okay, let's try that again. So typically, if you have a fast and reversible step, typically this means not. I'll eventually write this properly. Typically, this means not rate determining step. Okay. We haven't in these videos so far looked at equilibrium, but we're going to mention equilibrium briefly here, and we'll talk about equilibrium after the topic of kinetics in this class. So here, a fast and reversible process implies it's not rate determining, but it actually implies it is at equilibrium. So far, rate determining and equilibrium are opposites in this context. So if we take the latter idea of at equilibrium, what does at equilibrium mean? It means that the forward and reverse rates are equal. Forward and reverse rates are equal at equilibrium. Okay, so for now, without explaining what equilibrium means, let's just say it's a condition, and if you've met that condition, you can make this statement that your rate forwards and your rate reverse are equal. So we said that step 1 is at equilibrium, correct? Because step 2 is rate determining, so step 1 is at equilibrium, which is this one. So we essentially can say this forward event is going to be NO and O2 a product reactant. So we'd say rate forward is a rate constant forward, and then we've got the reactants. NO to the first order, O2 to the first order, and then the rate reverse, they call it R here, is the rate constant reverse, but now we're going backwards, so our only reactant going that way now is NO3. So it's going to be NO3 to the first order, and we can set those equal, so we set these two expressions equal, and that's where this comes from. Okay, so we've got this expression here, and then we isolate it by dividing both sides by Kr to isolate this. Why would we want to do that? We'd want to do that because it's an intermediate. Okay, are we sure it's an intermediate? Let's double check. I'd have to get rid of all my drawings. So just to double check, it's an intermediate. Yep, it's not present anywhere, but it is in our mechanism. It's produced in step 1, it's consumed in step 2, so it's an intermediate. And we said earlier we can't measure the concentrations of intermediates accurately, so we want to solve for them. So I can't measure NO3 accurately, but I do know I can measure rate constants and non-intermediates accurately. So now I've set my intermediate in terms of something that's not an intermediate. So whereas I can't measure U accurately, can't or cannot measure accurately I can measure this accurately. So there'll be occasions where you'd have to do this, and then you would then go ahead and put this in your equation. Why would we need to do this? Well, let me remind myself what the initial equation was, so I don't have to scroll in and do all my annotations. We were told that the rate determining step is step 2. So we were told that rate 2, so I'll put recall that the rate determining step was rate is K2 NO3 NO. So we didn't just isolate the intermediate, for the chemistry of it. We did it because we need to now calculate the rate. So now we can say that the rate is going to be K2 KF over KR NO O2. And all of this we can just write as another K. Let's call it K prime. And we've got something we can accurately measure. All right. Okay, moving on. This reaction should just do something similar. Oh, actually, no, this is a long-winded version of what I've just said. So my previous annotation, this is a different, no, I'm sorry, this is a slightly different equation. Same thing, slightly different equation. Let's go through quickly. Different equation, NO2 plus CO gives NO plus CO2. We know from experimentation the rate law is K second order in NO2. proposed mechanism is given here. We can see again that nitrogen trioxide is an intermediate. So we can see that this is produced here. It's consumed here. We've also got another intermediate. This is produced and then consumed again. And we know that we have intermediates in our rate expressions. So that's something we can't measure accurately. We ascertained that the rate determining step is step 1. Remember, the rate determining step is the overall rate. And we already knew the overall rate was second order in NO2. And it just so happens that the first step is also second order in NO2. So they are equal to each other. Problem is, NO2 is an intermediate, and that's no good. We'd have to do the same trick. In addition, we just mentioned here, like we looked at in our previous video, I think the one immediately previous to this one, 0 order. So if we say that the reaction is 0 order in CO, that means that CO, as long as we don't have a 0 amount, as long as we have a little bit, a non-zero amount of something that's 0 order, any further amount or fluctuation in the amount won't change the rate determining step. Okay, so yeah, clearly if there's no CO, if CO is in our mechanism but there's no CO in our observed rate expression, we just say it's 0 order in CO. Okay, so that's just to keep on your guard, to look out for that. Okay, moving on now to unimolecular reactions. This is a famous problem that's worthy of our attention. So unimolecular reactions. So in terms of collision theory, we think of at least 2 objects colliding, exchanging energy, reformulating atomic orbitals to make molecular orbitals or linear combinations thereof. But what happens if a chemical process is first order? That means that at the active site, you'd only have one such molecule, which would be a unimolecular reaction. So how does that happen? How can something collide without colliding with anything? So this would be, oh, I've done that thing again where I'll never know how to erase it. So give me a second. There we go. So I guess the conundrum here is how to collide without a collision. That's the problem. So we're not going to look at a specific example here, but there's just a specific example shown briefly just to give you an idea of what it might look like. So we take cyclopropane, and this all by itself can open up, the cyclic chain can open up to give a linear propene. And it's got some rate constant, and then it's first order in cyclopropanes. This is first order process is what an example might look like, but let's keep it more general and thereby more applicable. So collision theory, again, the problem is, how do you collide without a collision? Collision theory cannot explain unimolecular reactions because they're first order, not second order. So we only have one molecule at the collision site. Unimolecular reactions were correctly explained in 1921 by Frederick Lindermann, and later on contributions were made by Hinshelwood. So we are now going to look at the Lindermann-Hinshelwood mechanism for a unimolecular reaction. So take a molecule A, and it's in a sea of its own kind. So there's obviously, unless you have just one molecule, it's going to be bathed in its other clone molecules. So it can collide with itself, with another version of itself, to give an energetically excited version of itself, which we label with this asterisk here to mean energetically excited. And that process would have its own rate constant. If we looked at the rate of formation of the activated complex, it would be a rate constant Ka, a to the power 2. If we accept that this is a mechanistic process, these are elementary steps, we can read into the fact that we have a coefficient 2 here, and that would be second order in A. Okay, so that's straightforward. A could lose its energy by colliding with another molecule. So you can think of the reverse of this process. So A bumps heads with another A, one of them is activated, but then it can bump head again and then undo its activation. It can numb itself again. The rate of this deactivation would be dependent on the activated complex and the non-activated complex. So we've got A star here and A, and then we've got a new rate constant, Ka prime. The prime here just distinguishes Ka, this deactivated Ka from the original activated Ka. Okay, alternatively, we can say that A star, the activated A, could just shake itself apart to produce a product. And this would be a unimolecular process. So it's already activated. So in a way, we're kind of cheating. We're saying, how'd you collide without a collision? There was a collision, we just didn't look at it then. And now we're looking at post-collision, and we are not privy to the history of this molecule. So let's put it that way. We're not privy to its history. So we don't care what happens to it here, but we know that once it's activated, rather than just becoming unactivated again, it might do something novel and lead to another product. So we could have the rate of formation of this product would be a different K entirely, different process, so we'll call it KB, but then it exclusively depends only on the activated complex A. Okay, so that seems pretty reasonable so far. So why is this such a problem to be solved? It looks reasonable so far. It is reasonable, but it's not as simple as it looks so far. If the unimolecular decay alternative is slow enough, so if that last process, the activated complex becoming the product, is slow enough to be rate determining, the reaction will indeed be first order, as we saw. Problem solved. Well, not quite. Let's look at steady state approximation. So steady state approximation looks at everything that's happening at once. And although it's a dynamic process, if your dynamic processes all occur at the same rate, it looks like a pseudo-static process. So that's what steady state means. So if we look at everything that will produce A, then we've got rate constant Ka, A squared. So the original collision of A's give A star. So that's a positive contribution to A. But then we've got something that consumes A star. So that's why we have a negative sign here. And this is the reverse of the initial process. So we form A star with the first term. We go backwards and then decompose A star with this reverse term. Another way to get rid of A star is to do something entirely different and make that product. And it's negative again because it's a loss of A star. Now, all this is happening at the same time. If we assume steady state approximation, steady state means a net change of 0. So if we assume that the rate of formation of A is not changing, so it's a constant concentration, then its rate of formation will be 0. And this is an expression it's a steady state expression. We're going to transpose these negative terms by taking them over to the zero side of the equal sign and make them positive. So you can see we've just done that here. So maybe I can slow the video down a bit. So we just take these negative terms here and we just hop them over here to make them positive. And now we've got everything as positive. Okay. So now we can just start to do some manipulation of this algebraic expression. So again, we made everything positive. Now we notice that we have an A star here in this term and an A star here. So let's factor that out. So we can factor out the term A star, our activated compound A. And then we're just left with Ka prime and A, which is here, and then Kb, which is here. Now we can cross multiply to isolate A star, essentially by just dividing both sides by the thing in the parenthesis here, and we get this expression at the bottom as shown. So that's all pretty straightforward. So still not apparent from what I've said where the big problem is. Okay. So we've got this expression here with A star. So let's just look at the rate of formation of our product, or supposed first order process, which remember was Kb A star. Well, we now know what A star is, so let's plug it in. We know that we have Kb, and then A star is Ka, so we've added Ka here. And then in the numerator, we also have A squared for our second order process in A. In our denominator, we have Ka prime A plus Kb. So we've essentially just inserted A star here into our rate of formation of product expression here. And then there's the problem. We don't have a first order process. The problem is we could get away with combining all of these K constants just to give a brand new K. So here it's kind of squished in a bit, but this collection of rate constants could just be its own unique rate constant K. And I have an A in the denominator, which could cancel one of the A's in the numerator. So it looks like it's Ka, but I can't get rid of Kb. I want to make it equal to 0 to make it go bye-bye, but I have to see how I can make it go 0. I have to make assumptions and under certain assumptions. So that's the problem, is Kb won't go away. Okay. So let's scroll down one last time, see how we can get rid of it. However, it doesn't look like it's first order in A. That was our problem. However, if the rate of deactivation of A star by A is the fast process, so A's collide, one is activated, and then they can go back again and just mutually deactivate each other again. If that's the fast, let's say, equilibrium process, then it's not rate determining. If, on the other hand, if we assume that the actual shake-free Kb A star process is rate determining, then that would be much slower, correct? So if we assume this here, that the product formation is a lot slower and therefore rate determining compared to this deactivation process, then we can assume, therefore, that if we get rid of the A star from both sides, we get rid of this A star from both sides, we're just left with Ka prime and A, and then Kb. So we can assume that Ka prime A is a lot greater than Kb, because we've just gotten rid of a constant from both sides, and the constant was A star. If this is true, look back here. this is now a lot greater than KB. So under those assumptions, we can assume that KB equals 0. Okay, if KB is 0, we've cracked it, because everything else disappears and we're just left with a rate constant and a single A in the numerator. Okay, so that was what was proposed and accepted by Lindermann and then developed by Hinshelwood. And we know it today as the Lindermann-Hinshelwood mechanism. So at last, it's first order in A. Okay, huzzah. Okay, so here's an example of a calculation. Go through this quickly. It's almost identical to the previous one, but it's how a question might be asked in class. Suppose an inert gas M is present and dominates the excitation of A and the de-excitation of A star. Devise the rate law for the formation of product. So you can see we're doing the same process as in the example above. A collides with M. You get activated A plus M. You can reverse that. A star can hit M again. Same or another M, probably a different one, to give unactivated A. Alternatively, A star can just decay to get product. We have the rate laws for each of these processes. We have the steady state approximation again, where we have the formation and decomposition of A stars all happen at the same rate, so therefore they sum to 0. So we form A star with the positive term, we decompose A star with the negative and the negative, but because formation and decomposition happen at the same rate, the sums of the rates are 0. That's the steady state approximation. We transpose the negative terms to make everything positive. We isolate or we solve for A star. We get exactly the same expression as we had in the previous slide, although previously this M was an A and we had A to the second order. Same problem, KB, and we could make the same assumptions. If this, then KB is 0, and then we have no problem. The M's cancel, etc. Okay. So let's manipulate this expression a little bit to look at a different style of question. So far we know that the rate of formation of product is KB A star. So this is the rate expression that we've seen already. This is the rate law, and we can set them equal. And we already know this was the expression we had earlier on. And it's first order if KB is just so happens to be 0. Okay, so let's look at what the rate constant is. So we know that rate, we know it's first order, right? So we know it's Ka because it's a unimolecular. So because unimolecular. Okay. So if I split this A squared up into, if I actually flesh out the A and get rid of that square sign here, then all of this stuff here must be the rate constant, right? So that's all we've done here. So Ka, Kb, A in the numerator, and then Kb, Kb, and then Ka prime A in the denominator. That's our new K. So if that's K, all I do is tack on the second A, and I have my rate expression. Okay, so we've got the rate constant for this process. Let's invert. So let's take the inverse. So we just literally flip everything and we have this expression down here. So that's straightforward. And you can see the benefit of doing that now. We have a straight line equation that we can plot on an Excel package or another spreadsheet of choice. And we can get a nice slope. The computer will tell us we can get access to some of these rate constants. Okay, so that's great. So for gaseous reaction, the concentration A could be replaced by its partial pressure, PA. So this would be, well, if it's unit, I've done that thing again. So I keep forgetting I have to click on this first. Okay, so this would just be the pressure, I guess, because there are no parts. So this just be the pressure of A. Okay, so instead of the concentration of A, we can just replace it with the pressure of A down here if it's gas. So that's reasonable because of the proportionality. Okay, so for a gas at two different pressures, PA and P prime A, we would just have an expression for 1 over K for one of the gases, 1 over K for the other gas, and then all of these constants, which are constants for A, they would, they're temperature sensitive, but they're not pressure sensitive. So these would cancel. So can cancel since proportional to T, but not proportional to pressure. And we're not changing the temperature, we're just changing the pressure. And so we can have this expression down here. And now we're just going to plug some numbers in here. So let's see on the next page what that looks like. Okay, so question. The effective rate constant for a gaseous reaction, which has a Lindermann-Hinshelwood mechanism, is 2.50 by 10 to the negative 4 reciprocal seconds at 1.3 kilopascal. And 2.10 by 10 to the negative 5 reciprocal seconds at 12 Pascal. Calculate the rate constant for the activation step in the mechanism. So the activation step is Ka. We are given the K and the K prime, and the Pa and the Pa prime. So we're going to solve for Ka, and we do that essentially by cross-multiplying. The Ka goes upstairs, what is on the left comes downstairs, and we've isolated Ka. Now we just plug in the variables, and we have a calculation. So the activation rate constant is 1.9 by 10 to the negative 6 reciprocal Pascal reciprocal second. Does the answer make sense? Yes. We would expect the answer to be the Ka to be less than the K or the K prime, correct? So makes sense since we know that Ka should be smaller than K or K prime, right? Because we already said that Ka is not rate limiting in our previous discussion. So the fact that we have 10 to the negative 6 makes sense because 10 to the negative 6 is a smaller number than either 10 to the negative 5 down here or 10 to the negative 4 down here. Okay, so that all makes sense. Okay, the final topic in this video is to look at just the general Michaelis-Menten mechanism, which is very descriptive of biological enzyme function, and is very important if anyone is headed to medical school or what have you. Explains many biochemical processes. Okay, so let's say we have an enzyme, enzyme. Yeah, we have an enzyme, I'm sorry. So let E be enzyme, let S be substrate, ES is the loaded enzyme. So loaded enzyme, and P is product. So this is the fast step because it's at equilibrium. Again, until we get to equilibrium, I'll try and be quick about it, but this implies equilibrium, these funny single-headed reversible arrows. So obviously this is the slow part, and this is the rate determining part because it's slow. Okay, so you have an enzyme, it loads with substrate, it can form an intermediate, that intermediate can unload again, or it can form product. Okay, so let's look at the steady state approximation here. Oh, first of all, we know that the rate or the velocity of the reaction, so let me get all my annotations back, so I wasn't ready to get rid of them yet. Rate in Michaelis-Menten kinetics is often called V, so you can think of V as velocity of reaction. It just historically called V a lot. So the velocity of the reaction or the reaction rate, obviously, if I'm trying to make product, is the slow step, which is KB, first order in ES. Okay, now we're ready to get rid of our annotations and scroll down a bit. Okay, steady state approximation. The rate of change of this loaded enzyme structure here is this term positive because we're forming ES, this negative term because we're consuming ES, and this final term is negative again because we're consuming ES. But the production of ES and the removal of ES is equal. The rates of those processes are equal at steady state, so they sum to 0. We can transpose the negative terms over to the other side to make everything positive. And now, like we said earlier in this video, we're going to isolate the intermediate ES because we can't measure it accurately. So we're going to solve for it in terms of things we can measure accurately. Okay, so I'll go through this pretty quick. It's very straightforward, and you can pause the video if necessary. But we're going to pool like terms. So we're going to drag essentially the rate constants on one side, keep them together, and then we just have ES on the other side. So we have this new simplified expression here. And we're just going to relabel this parenthesis here, which is a ratio of rate constants, as the Michaelis-Menten constant. Notice here we've called this accumulation of lowercase k rate constants an uppercase K Michaelis-Menten constant. This Michaelis-Menten constant is an example of an equilibrium constant. It's an equilibrium constant. Equilibrium constant. And we'll see that in subsequent videos when we look at equilibrium, but not today. But there's clearly a link between kinetics and equilibrium, and that's something I'll point out in later videos. Okay, so we're just doing some basic algebra here where we know what we want. We're trying to isolate ES. So we've now tidied this up a bit. We've replaced that awkward, clunky collection of rate constants by this equilibrium constant, Michaelis-Menten constant here. Let's see what the Michaelis-Menten constant is. Okay, so we're going to come back to this when we look at equilibrium. In subsequent topics, we'll come back to the fact that it's a ratio of concentrations, but not in this video. Now, this looks dark. I actually had this on colored paper, and when I copied it, it left this fuzzy gray appearance, but I think it's still readable. So rather than have to rewrite it again, along with all the other things I have to do, I'll just talk you through it. let's make an assumption. So this starts off with an assumption. Let's get up to here. So we're going to make an assumption. The total amount of enzyme, which is ET, is equal to the free enzyme plus the loaded enzyme. So total enzyme is free enzyme plus loaded enzyme. I mean, what other state of enzyme could you have? So that's a reasonable assumption, or maybe assumption is the wrong word, a declaration. So it's probably more better thought of as a declaration. Okay. So therefore, we can solve for E. We just take the ES to the other side. So therefore, the free enzyme is the total enzyme minus the loaded enzyme. Okay. If we look at our previous expression, and just so I don't have to keep scrolling, I'll look at what I had on that previous page because I have a printout here. So on the previous page, we had this. So yeah, we had this. We had ES equals Michaelis-Menten constant ES. All right. And now we've solved for E. So I'm going to plug in this stuff into E here. As you can see here, so I've got ET minus ES, and then I've got that residual S is equal to the Michaelis-Menten constant, and then the loaded enzyme ES. All right. Let's multiply out the bracket. So I've got to multiply the ET by the S and then the ES by the S. So we do that here. So the ES by the S and then the ES, the ET by the S minus the ES by the S. Okay. And then I can take this negative term. So I can take this negative term here and I can transpose it over here and make it positive. So I've isolated a term on the right that has a factor of ES in common. So I can factor out that ES. So factor out ES because it's present here and here. So we factored it out. Okay. Now I'll have to scroll. So now we can finally isolate ES by dividing both sides by Kn plus S. So now our overall goal has been met. We've got our intermediate that, remember, we cannot measure accurately in terms of things we can measure accurately. Because total enzyme, I know that because I put it in the reaction, right? So I have control as the scientist, I have control over that. I can control the substrate I add, and this is ultimately solvable, this ratio of rate constants. So everything on the right is knowable, and the stuff on the left is not knowable. So I've set the knowable in terms of the unknowable, and therefore I've overcome that problem. Okay, let's look at the consequences of what we've done. So going back to what we said initially, the overall rate is KBES. Now we've got an expression for ES and we can put it in. So thusly, now if we look at this item here, if we would expect, so we'd expect V to equal Vmax. So we'd expect the rate to become a maximum when the loaded concentration of enzyme is maximized. Well, that's when it's equal to the total enzyme. Okay. So if that's what we have here, then we can replace this by the word Vmax. Okay, so that's a pretty reasonable expectation. And that's exactly what we have here. We replaced this thing with Vmax. So we have finally our Michaelis-Menten expression, which here is that the rate is Vmax S over Km plus S. So well worth remembering that equation. Okay, but what can we do with it? So this again is, it governs much biological reaction chemistry, so it becomes very useful for people in biology, etc. The problem is that as it's composed right now, it's not in its straight line form. It gives this curve. So let's try and manipulate it a little bit to make a straight line curve. And we're going to do that by converting it into a Lineweaver-Burke plot, which is going to be a straight line expression. So let's have a look at how we do that. So we take our Michaelis-Menten expression here. So the rate is the maximum rate multiplied by the substrate concentration divided by the Michaelis-Menten constant plus the substrate concentration. We essentially take everything here and divide it by S. So we take our numerator and divide by S. So you can see I've put an S in the denominator here. We take the denominator and divide by S. You can see why we've done that. It cancels the S in the numerator and in part of the denominator. So we get a more simple looking expression, which just has Vmax as a numerator. And then we get a 1 here plus Km over S. We get something that looks a lot more simple. So let's start off with that simple expression here. We're going to invert. We're going to take the inverse expression. So instead of V, we're going to have 1 over V. So we just literally flip everything, and then we can rewrite it. We can see we have 1 over Vmax, and then we have Km over Vmax, and then 1 over S. So if I get this clunky thing to scroll for me, then you can see that that's our y is mx plus b expression. So again, it's straightforward to do it. And we can plot 1 over rate on the y-axis. We can plot 1 over s on the x-axis. The slope is the Michaelis-Menten constant over Vmax. The intercept is 1 over Vmax, so we can ascertain exactly what the maximum rate possible is. So that becomes very useful. And again, we can solve for the Michaelis-Menten constant here. The Michaelis-Menten constant, we can see here if we extrapolate back, we can get access to it here. So we're looking for x when y equals 0. So that's why I've put here at y equals 0, we solve for x and we get this value here. So you can take a second to scribble that on a piece of paper and pause the video if needed. The value of the rate constant is calculated as follows. The y-intercept from the Lineweaver-Burke plot, etc. Okay, so that's straightforward. What might this look like in the lab, though? One process you can use is the stop flow technique, which, essentially the way I've drawn it here is a few syringes. So we can have enzyme in one syringe. We can have substrate in another syringe, and they both feed into a chamber where they can mix and form the loaded enzyme. and then that has then the option of producing product. We can detect formation of product via different means. It could be a color change, it could be an indicator, what have you, or spectroscopically somehow. And then the product goes into a collector syringe. Okay, so that's practically how you might get access to that. And here's a question. This is a pretty common question. Calculate the substrate concentration required to decrease the rate to 50% of the maximum rate possible. Okay, so we start with our straight line form of Michaelis-Menten, the Lineweaver-Burke form, which was 1 over V, Km over Vmax, 1 over S plus 1 over Vmax. We make the declaration that when the rate is half of the maximum rate, then we have V becomes Vmax over 2. So if V becomes Vmax over 2, well, this 2 is going to flip back around, and that's where you get this from. So we get 2 over Vmax is Km over Vmax, 1 over S plus 1 over Vmax. We can take this 1 over Vmax to the other side, and then we have 2 over Vmax. This becomes minus, so minus 1 over Vmax. Well, that just becomes 1 over Vmax. So now we have 1 over Vmax is equal to Km over Vmax, 1 over S. And we can see that they both have a Vmax in common. So we can get rid of the Vmax. We can multiply through by Vmax. So we have this expression here, Km over S is 1. We just cross multiply. So Km is numerically equal to the substrate concentration. And this is a general result. So to answer the question, calculate the substrate concentration required to decrease the rate to half of the maximum rate. It's just numerically equal to the Michaelis-Menten constant. So let's see how many more notes we'll discuss in this video. Just a couple more pages and then we'll conclude this video. So here's another Michaelis-Menten question. In a particular enzyme, on white paper this time, that's why there's no shading. In a particular enzyme catalyzed reaction, Vmax is measured to be 0.2 moles per second. Km is measured to be 5 millimolar. Assume that the enzyme shows standard Michaelis-Menten kinetics. What's the reaction rate when the substrate concentration is only 10 millimolar? Okay, so we have our Michaelis-Menten equation here. We plug our numbers in to solve for rate, and we get a value of 0.133 moles per second. So that's another example. Plug in some numbers in. So you can practice that and pause the video and practice that at your leisure. This question just says plot the information you've just seen. Here's a little plot. Again, we have that curve for the Michaelis-Menten rather than the straight line. The straight line is the Lineweaver-Burke form of the Michaelis-Menten. So again, you can look at this question is just a graph recognition. Which form of the equation do I have? If I have a curve, it's Michaelis-Menten. If it's a straight line, it's Lineweaver-Burke. Okay, and this is our final question and slide for this video. The enzyme catalyzed conversion of a substrate at 25 degrees Celsius has a Michaelis-Menten constant of 0.045 moles per liter. The reaction rate is 1.15 by 10 to the negative 3 moles per liter per second when the substrate concentration is 0.110 mole per liter. What's the maximum velocity of this enzymolysis? Okay, so we've got to solve for Vmax. We start off with the Michaelis-Menten equation. We cross-multiply to isolate Vmax, so that's straightforward. And then we just plug in our numbers. And we get a Vmax of 1.62 by by 10 to the negative 3 mole per liter per second. That's the last notes for this video, so that will conclude this video.